So, Dario, you already, shared your slide. Okay. So slides. Okay. So, so let me introduce, now, the next speaker, Dario Poletti. Okay. So we will talk about neural network, quantum states, and transfer learning. So again, around, 5:30, I will say 5 minutes left. Okay. Dario.
Okay.
Okay. And then we will go for some questions, hopefully. Okay.
Okay.
So the floor is all yours. Okay.
Thank you, Christian. Thank you to all the other organizers for helping to putting this together. And hopefully we can do it also physically eventually. So today we wanted to touch different topics, give you an overview of different techniques that are very useful to study, also materials, and that they can be used on the high performance computing. We looked at PEPs, we looked at quantum Monte Carlo. We'll see more about quantum Monte Carlo later. And now I wanted to tell you about neural network quantum states, which is a more recent numerical tool. And it will be quite introductory. And then towards the end, if time allows, we'll talk a bit about some of the work that we did in collaboration with people here in Singapore and in France. Okay, so let me start. If you move, okay. I also would like to advertise Thursday, like a kind of a satellite event. Giuseppe Carleo, who kind of started this field in 2016, together with Matthias Troyer in a science paper, the first use of neural network to study many-body quantum states. He's going to give a colloquium at the CQT, so you can register, you can try to attend this. I think it will be very interesting, and he's definitely a star in the field. Okay, so the plan of today is to tell you a bit in general about neural network quantum states, then a bit more specifically about restricted Boltzmann machines, which is simple type of neural network, quantum state neural network. Then I will, if time allows, I will tell you about the restricted Boltzmann machine and transfer learning. So it's a technique that can help get quicker results and better results. Okay, and then my conclusions. So let us start. Feel free to interrupt, ask questions if you have any questions. Okay, so neural network quantum states can represent probability distribution. Actually, they can represent any functions you want. So why not using neural networks to represent wave functions? And this is what was done in 2017 in the science paper by Carleo and Troyer. Where they show our neural network, in particular, in that case, it was a restricted Boltzmann machine, can be used as a variational ansatz for many-body quantum system. And this opened quite a big amount of research. So there are various questions that I would like to address in this introductory part. They say, why now? Why are we doing this now and not before? Or what is the time is mature for this? And how are neural networks used in physics in general? And then how effective are neural network quantum states? And what is the main working principle of neural network quantum states? And what kind of architectures people have so far investigated for this purpose? Okay, so I hope this is fairly general, can help most people. So why now? And so more and more, if you look around, we see artificial intelligence and machine learning everywhere in many of the activities we do and in apps that we use. And some applications that have shown incredible advances have been in natural language processing, in image recognitions, but also in games. And there is this famous application of AlphaGo that was able to also win at Go quite in an impressive way. So this is from one point of view, but what was behind this? And there have been great progress from deep neural networks. Okay, so from like algorithmic point of view, let's say, and also in hardware. Okay, the GPUs, better GPUs and more available GPUs that also played a big role in the progress of the field. So all of this then motivated physicists to say, okay, why don't we use this more for what we do, since it seems to be working so well in many other things. Okay, so where is it used? Where are they used in physics? Okay. And we can see they've been used. I can first of all mention there is these two nice reviews that talk about this topic, and I think this review by Carleo and others, and it really goes through many different fields in which neural networks are used in physics, and you can use them to guide your experiments, figure out which parameter portion of the parameter space to explore earlier than later, so that maybe you can find some nice effects. You can use it to in particle physics and cosmology. It's been used for a long time to analyze data from from the experiments, recognizing phases of matter. You can use for quantum states and try to characterize the states or even processes, like open quantum processes. You can use for quantum error correction, and also find the ground state of Hamiltonian, which is something I'm going to talk about today, but also to study the evolution of the system or find the steady state of open quantum system. Or even algorithmically, if you have a routine that you may be able to accelerate, like for example, some portion of the MFT by using neural networks somewhere. So they're used in many, many places, okay? And today I'm just gonna talk a little bit about a portion about finding the ground state of Hamiltonian, okay? But there are many other things that could be done. Okay, so what about how effective are they? Why we can use them? Okay, so it was shown by Chen and others that any state described by matrix product tensor networks can also be described by restricted Watson machines. So this already tell us that if you think about the things that Guochu discussed before in the first talk, then that this can be represented also with neural networks or restricted Watson machine. Okay. So this is from a representation point of view, okay? And what is also interesting, and was shown by Deng and others in a PRX paper in 2017, is that because of a peculiarity we'll show later, basically long-range couplings between different terms, they can also represent states which tensor networks would have a hard time doing, which are volume law states, so states which have a very, in which the entanglement scales as the volume of the system, and not just as the area law state. So the potentiality is there. Now the question is whether you can reach these ground states or follow the states properly, and how effectively you can reach them. Okay, and then the effectiveness of how this algorithm depends very much on the problem that we are studying and which neural network we are using to study them. Okay, so I will give you some example of some of the things that have been done. Let's say, for example, I want to compute the ground state of a system. Some of the hard problems are to compute ground state of frustrated systems. And here, I think the state-of-the-art calculations for this famous two-dimensional problem, J1, J2 frustrated system, is a work that was done by Kenny Chu and others in 2019, where they compare results from neural network quantum states to variational Monte Carlo, DMRG, and quantum Monte Carlo. Okay, let me try to describe this figure to you. So on the y-axis, you have the energy minus the energy of a convolutional neural network, which is what they used. Okay, so you have 0, obviously, for the convolutional neural network. And for all these points, if they're above the 0 line, it means the convolutional neural network found a state which has lower energy. So in theory, it's closer to the ground state. And you see that in general, the convolutional network is below, except in this region here for J2 close to 0.5, which is actually the hardest region to study, where frustration is even more important. So in this region, while overall you can see the CNN convolutional neural network can be competitive with other 2D methods, we find that in some regimes, still methods like DMRG give the best results, okay? But at the same time, we can say the neural network quantum states is a much, much younger algorithms compared to DMRG. So maybe there is room that eventually they become better, we don't know. And that's why we're studying. Now, if we want to look at time evolution as well, we can do time evolution with a neural network quantum states. And this is also data from the paper by Carleo and Troya in 2017, so the first paper on this topic. And you can see that if you look at some quantum properties, they can follow the exact solutions or the DMFG solutions very well, except maybe for some long time, you see where in the region that I put a red box here, we can see deviations from the neural network quantum states and the exact solution or the DMFG solution. So it seems to that it can be used, but there is still work to be done. There has been recently more works by Heil and others, and also other groups, competitors groups, and they have improved significantly the time evolution, but there are still some limitations, and that's also why life is fun sometimes. If it was too easy, it would not be fun. Okay, so, but what is the idea behind the neural network quantum states in general? And the main idea is the variational principle. And here I'm talking specifically for computing ground state. To do time evolution would be a similar approach. We'll minimize the distance between a predicted wave function and the one that you want. Okay, so this is the energy of a system, and we know that if we have a wave function, we minimize this, we can approach close and close to the ground state. So we can take the energy and we can rewrite this expression like this in some basis, okay, where x is whatever basis I choose, okay. And theta here represents the parameters of the neural network, and now we use the neural network to represent psi. Okay, so now if we, with a little bit of rewriting of this thing, we can bring this sum all the way here in the red box, and we can multiply and divide by psi of x, and we get something like this. So modulus of psi modulus square divided by some normalization times this term in the blue box. So it's just a rewriting of this, assuming that I can divide and multiply by psi of x, which is fine. And then I can rewrite it like this. This portion here in the red box is basically a probability of having a certain configuration. And then I have a quantity which we call ELOC, local energy, okay? And so this is in essence, from here on is in essence variational Monte Carlo. We have this ELOC, which is this portion here, what was in the blue box, okay? And then we sample this, okay, over a wave function, which is what the neural network is at that time for the given values of theta, okay? So we have some values of theta, we put a certain configuration, we get a complex number psi, and then we use this complex number psi to try to compute the energy, and then we just do some gradient descent to minimize this energy by changing the parameters theta of the neural network. You see, basically what we're gonna sample this value ELOC over a probability distribution of psi. So this is in a sense variational Monte Carlo, and that's the main idea of neural network quantum states. Okay, is a very powerful ansatz, and then you do variational Monte Carlo on it. Okay, so what kind of neural networks have people used so far? So to the best of my knowledge, there is, of course, a restricted Watson machine, which is here on the top left. Then there's been works on multi-layer perceptron, okay, in Shanghai. Then convolutional neural networks, the paper that I mentioned before on the frustrated system was using convolutional neural network by Kenny Chu and others. And recurrent neural networks also have been used, for example, in this physical review research of this year. As you can see, all the works are very recent. It's a really, really new area, okay, and there's still plenty to do in the field. I have to mention that there are already some packages you can use online. For example, Carleo and Chu is one of the main developers, developed this netcat, which you can go and download, and you can start to play and try to understand how to use various type of neural networks. It's not only the architecture that you use, but also it depends also on the optimizer that you use to go and find the minimum or the samplers that you choose. So there is a lot of things that you can play around, and you need to find the ones that gives you the best gains, and try to find a way to do it systematically, or try to find what works best for what kind of problems. Okay, so it's a very there is plenty to do. Okay, so now I would like to go a bit more in the specific. Okay, maybe there is a question. Let me check in the chat. Okay, no, nothing in general. Okay, so in the specific of restricted Boltzmann machines. Okay. So this is the first neural network people have looked at, and let me try to describe to you how it works. Okay. You have a visible layer and a hidden layer. Okay. The visible layer, for example, it's a spin configuration, and you could have spin up and down, and so you could have 1, 0, or 1, -1, -1, 1, 1, -1, something like that. Then you also have a hidden layer, and you think of it also as like spins, for example. And then you connect them. How do you connect them? You connect them with this matrix WJI. And what is interesting here, and it's very important, all the visible node, each visible node is connected to all the hidden nodes, but it is not connected to any of the visible nodes. And the same way, all the hidden nodes are connected to each and every one of the visible nodes, but they're not connected directly with each other. Okay, this seems a bit artificial, but it really helps significantly getting good expressions, and then simplifies your life significantly in the computations. In the same way, you can think that X1 talks to HL, which talks to XL. So indirectly, you are connecting X1 to XL, but doing it this way through the hidden layer simplifies significantly your calculations. And then we can also put some effective biases on the various hidden and visible nodes as well. Okay, so this is also what I mentioned already. Now, the expression, mathematical expression for this restricted Boltzmann machine is given here, and it was you found decades ago. And it's you have an exponential of aij xj. So some kind of like magnetic field for your spins, something also for the hidden layers, and then some coupling between them. And this is the restricted Boltzmann machine is a function of whatever configuration you have in the visible and hidden layers. So I try to highlight here is the restricted Boltzmann machine is function of x and h. Okay, and then you have all these parameters that you can change. Okay, and you want to optimize over these parameters WAB, so that this eventually will help you to describe your wave function. How do you get to the wave function? Well, you can sum over all the H's, okay, all the possible configurations of the hidden layer. You sum over all of them, and if you do that, you get these answers. So basically, this is the answers of the restricted Boltzmann machine after you sum over all the possible configuration of the hidden layer. And this, you can use it to represent your wave function, or if you know that your ground state is real and positive, you can use it to represent your the probability, the modulo square of psi already. Okay, so it depends. This is not the most general solution, but it works for some problems. And the most general is to say, okay, this function that I get out is going to be a psi. Okay, and then I will. This is my answer, and then if this answer works, all the better. Okay, this is for restricted Boltzmann machine at least. Okay, now these two ingredients are all you need to describe and do work with the restricted Boltzmann machine. You have your network, and then yes. Okay, I thought there was a question. You have your network, and then you have and then if you are sum over the hidden layers, you get your representation of wave function, and then you have a way to compute the energy, which is by sampling this quantity that you compute depending on your psi x. You sample over the distribution that is given by the RBM. So this is the idea. And once you do this, you just minimize and you try to find the optimal values of theta to find the energy. Okay, I say just minimize. Well, of course, there is some work to do these codes and so on, but the idea is not out of this world. Okay, so
Dario, 5 minutes.
Yes. Okay, so I will go through a bit of the application now for a few of the things that we have done. It should be fine in 5 minutes. Okay. Okay, so this is a collaboration that, as I said, between Singapore and France. France, there was the Université Côte d'Azur, Infini, CNRS, and in Singapore, there was Majulab, SUTD, and NUS. Okay, and so you see here all the main actors. Some of them are also here, like Christian, the chair of the session. And the idea was okay. I want to find the theta, so the parameters of the restricted Boltzmann machine as quickly as possible and as accurately as possible. But that may not be so easy if I always start from some random values. Okay, so I want to start from some good values, and so we started to think about doing transfer learning. And transfer learning, the idea is used in supervised learning very much. So you train your neural network with something similar. Even let's say you want to categorize dogs, you train it with cats. Because you have many photos of cats, but you don't have so many photos of dogs. But they have a lot of similarities, cats and dogs. So you train it first with a lot of cats, and then you refine it with dogs. And then at the end, it's like you have trained your neural network with plenty of dogs, and it will work very well. Now you can go beyond this, and you also use it for supervised, unsupervised learning, like what we're doing. Optimization, basically. So we train our neural network with a small system, and then we want to go to a larger system size and try to transfer some of these weights that we found for small system and see whether we can get better results already at larger system sizes. So if I were to explain something, this is the main thing that the idea I would like to explain for this. So suppose I think about my WJI, this matrix here, that I would need to find to know what my state, my wave function. So I have a visible layer. I have certain number of nodes here in the visible layer, a certain number of nodes in the hidden layer, and then I can try. I need to populate a larger matrix, and you can try different schemes. And so what we did, we tried various schemes which are physically motivated. How to, you start from a 4x8 matrix, and then I need to populate a 8x16 matrix. But how do I get the values from the 4 times 8 to 8x16? So we try different strategy, which is called 1-2, 2-2, L2, L4 tiling, where basically we are copying the system, each row twice, or a group of 2 rows twice, or the whole system twice, or maybe we go straight away to 4 times the size and reproduce the system many times. So these are some ideas of how to do this. And the rest, I will put some Gaussian noise, okay, just not to set it to 0. If you set it to 0, it's a bit of a problem. And, this is kind of physically inspired, because one way you can think of doubling a system, let's say you start from an antiferromagnet like this one here, okay, and I want to double, I could say, okay, each side, I can take a pair of them and I can reproduce it, and then I take another pair, I can reproduce it. And this is the idea of the 2-2 tiling. Or you can try to you can try different strategies. Like I take one single site and I make it 2. Okay, you can see this already will not work very well if you want to generate an antiferromagnet, but it can work very well if you want to generate a ferromagnet, which is a bit what we find here. Okay. Also, we found that decoupling these halves it really helps a lot the performance. So maybe I skip this and I show you some of the results because I guess I have 2 minutes left.
Yes,
and
even one.
Even one. So
no, but it's okay.
No. I just want to give the main idea. I think the main idea is here, and we tried with different Hamiltonian and different strategy, and we looked at the time that it takes to get to convergence and the quality. And we see that, for example, for antiferromagnets, some strategies do not. So the blue line is if you don't do anything, okay? And the green line is trying some strategies, and red line some other strategies, and so on and so forth. And we see that some strategies work significantly better than, you see here, and here, significantly better than the cold start, which is this one here. So there are ways to speed up our calculations significantly. And now maybe I will just go to the other plot here. Here is about the quality of the state, how close you are from the exact solution, since we are very accurate solutions. And here we see this is the blue ones are the cold start. So in some regimes, like paramagnetic regimes, it works. It doesn't matter if you do the transfer learning. But in other regimes like this one, doing transfer learning gives you much more accurate results than not doing anything. Or even here, for example, a ferromagnet in Heisenberg, if you do transfer learning, we can get orders of magnitude better ground states if you don't do transfer learning. And this is the message that Mindy wants to give to you. Now, what transfer learning you want to do, it's something that we have some insights, but more analysis needs to be done. And then I just go to the outlook, because I would like to say a few words, more general words in this portion here that I really would like to address. So there are many lines of research at the interface between machine learning and many body physics, and a lot has to be done. And I would like to stress some things. What are the limits of efficiency, effectiveness in finding the ground states? Okay, and will eventually NRQS become the way to go for 2D and 3D systems? We don't know. We have already some very fantastic methods like quantum Monte Carlo, right? And DMRG for certain systems or PEPs work really well. So are they really competitive? Will they be competitive? This is still something that we need to figure out. Are there limits for time evolution? And can we use physically inspired architectures, okay? And also optimizers so that we can improve our performance? And then maybe more general questions is, can physics teach us to do better neural networks, come up with nice neural networks that can sort certain type of problems and help us to interpret the results of the neural network, which is a big important question. If you want to use results from machine learning, which are important in life, like things about medicines and so on, you would like to be able to understand their results and interpret them, and maybe gaining a physical intuition of their performance. This could be really helpful. Okay, and I stop here. Sorry for taking a bit too long.
Okay, thank you, Dario, for this very nice talk. Okay, so the session is open for discussion. Any questions? Okay, let me shoot first. Okay, I won't ask question about the work itself because I was a member of that work, but just a general question also. As far as I see, I mean, the hidden layer is always, I mean, removed in a way because you trace over, right?
Mm-hmm.
So, but the hidden layer inside reminds me of ancilla states in a way. Okay. Mm-hmm. So do you have any ideas about how to effectively or differently use, I mean, this hidden layer to extract, I don't know which kind of signal or whatever, with your quantum information experience?
Okay. Well, I'm not a quantum information expert, but well, I think maybe what you're trying to say, if I interpret it in the things I'm more comfortable with, is like, is there something similar to entanglement entropy, or when you split a tensor network that can be related to this?
Fisher or whatever, okay, you know, yeah, okay, information that I can extract, okay, find some way.
Yes, so I think by studying the distribution of these Wij's, you can learn quite a lot. And actually, this is something that I didn't show in detail. Something that we were seeing also in our work. We were looking at how these Wij's are populated, and seeing how they're populated, and maybe also looking at off-diagonal elements can tell us a bit about how the correlations spread throughout the system. This is the first thing that comes to mind. I do not know on the top of my head of analytical results or theorems that talk about this. There is, though, a notion that the number of hidden layers, the ratio of number of hidden layers compared to visible layers, how it helps to increase the representability or the obviously that there is work on.
Okay.
I have a comment.
Please, yes.
Sorry, quite here.
Yeah.
But if you have ancillas, then you will differ from the current answer, because when you trace over the ancillar states are not classical states. So there will be a difference with the current answer. So Dario want to comment on that.
Okay, so I took Christian's question simply as you have more of these HLs and you look at the occupation of the WIJs, okay? And I think what you're thinking about is that here you put qubits, right?
Yes,
Yeah,
because
absolutely.
this is precisely what ancillars are meant for.
Yes, I agree.
So,
I agree.
Yeah, I'm not sure what is the what has been studied. I don't think it has been thorough studies on this yet.
Okay.
Yeah.
I don't see any other questions. Final call for questions before we move to the last speaker. No? Okay, so then, I mean, Dario, thank you. Okay, I think we should discuss more about these ancillary things. Okay, but we do that later. Okay, okay. Okay, so now, I mean, my pleasure is to welcome Michele Casula. So maybe Michele can share his screen.
Yes.
Yes, okay, so.
Good. Okay, good. So thanks.
So
yes.
I don't need to introduce your title because it's everyone can read, right? Okay, so just again the same. I mean, it's around. I mean, 6. I will tell you 5 minutes to go. Okay, and then we will have the 5 minutes, and after some questions and see. Okay.
Good. Okay.
Okay, so please.
Okay, so first of all, thanks to the organizers for giving me the opportunity to present this overview on quantum materials, and also to show you an approach we developed recently to tackle quantum materials from first principles. So this is the outline. So first of all, I'd like to give you the definition of quantum materials I'm going to use in the presentation, which differs a little bit from the one we have seen so far. And it's more oriented towards material science or materials properties, more precisely. And so the second point of the outline is to show some remarkable properties of quantum materials. The third one will be about the challenges, both theoretical and computational, these materials pose. And finally, I'll show you the quantum Monte Carlo way to solve them. Okay, so quantum materials in my own declination. So they're also called quantum crystals in the solid state phase. For me, those are materials where both electrons and nuclei are quantum particles. And the focus here is to describe those materials in terms of first principles, namely starting from the Schrödinger equations, where we have the kinetic term for electrons, the one for ions, and the full interaction between electrons and ions through the Coulomb potential. So quantum materials in this category are more specifically described by those where nuclear quantum effects, NQE, are strong and strongly affect their properties. It means that nuclei should be light, because we know that for light masses, nuclear delocalization is very important, is very strong. And nuclei are no longer point-like particles, like in classical world, but they acquire a spread. So they became more a wave than a particle. So though in these materials, the particle wave duality applies. And as these nuclei should be light, the lightest element, of course, is hydrogen. And so you would guess immediately that the hydrogen-based materials belong to this family. And just a comment, a side comment on that, as hydrogen and helium constitutes more than 99% of the hadronic matter in the universe, you would imagine the importance of quantum materials overall to describe the properties of the overall properties of materials in the universe. Although I should say that to appreciate quantum effects, you should be in some specific conditions. And anyway, to introduce the importance of these materials, not only in terms of constituents, but also in terms of properties, let me go through this plot here, which shows the critical temperature for superconductivity discovered over the years, starting from the early age of superconductivity, early 20th century, till the latest compounds. And you can see here a spot, the upper corner, the upper right corner of this plot. There is a point which is very important for me, because this point represents the highest critical temperature for superconductivity discovered in 2016. So it was the plot up to date till 2016. And this belongs to a hydride. So a quantum crystal, a quantum material. And it's in particular, this hydride is the sulfur hydride, H3S. And this basically, the crystal is a cubic structure where hydrogen bridges between two sulfur corners. And this features the highest critical temperature known till 2016, but with a caveat that this high critical temperature happens at very high pressure as well. In this case, it's about 150 gigapascal. So this was a revolution, because there is another way to reach high critical temperatures, not based on strongly correlated systems in terms of strong local Coulomb interaction like Hubbard one, the Hubbard one. But there is another way, and this way is still amazingly related to the BCS, the original BCS theory of superconductivity. And it's related also to the quantum properties of hydrogen in these materials. So this basically ignited a rush in the community, and soon after, in 2019, another hydride was discovered, the lanthanum hydride, lanthanum H10, with even higher TC, 250 Kelvin, reached at 188 gigapascal. And so this is a clathrate structure, where now the rare earth is in the middle of the cage, surrounded by hydrogens. And that was predicted by BCS theory in 2017, and discovered 2 years later. That's not the end of the story. And so this field is very, very fast, and goes very, very fast. And the latest claim is basically was published a month ago, where they claim to have reached the room temperature superconductivity finally, after a long quest, in a compound which is sort of an alloy made of carbon, sulfur, and hydrogen. Even in this case, the nearly room temperature superconductivity happens at very large pressure, 250 gigapascal, and there is a lot of room for improvement, because the ternary alloy is actually unknown. The structure is unknown, although the stoichiometry should be known from the synthesis of the compound. Okay, so high TC would be beneficial in many sectors of our everyday life, going from energy to transportation to medical imagery, and also to science as well. Of course, the challenge is to predict new compounds, possibly with much lower pressures, based on this idea of exploiting quantum nuclear effects to highlight, to enhance these properties. Another class of quantum materials, in my definition, is the one where hydrogen bond is dominant, like, for instance, water, and like aqueous compounds. Hydrogen bond structure structures water in a non-trivial way and makes the well-known network within the water, and also is the base to explain, to hopefully explain its remarkable properties, like a liquid denser than a solid, high melting and boiling points, high dielectric constants, and also the very high ionic mobility of hydronium and hydroxide in water. All these properties are very hard to explain and very hard to predict in a robust and quantitative way. Just to give you sort of a broader overview about the challenge we are faced to in these materials, a sort of talkative and illustrative plot is to show the phase diagrams. You can see here the phase diagram of hydrogen and the one of water. Those are extremely rich, extremely complex. Despite the simplicity of the unitary bricks, hydrogen is the simplest element, and water is also rather simple. And so this complexity is somehow related to a common origin in both cases. And this is basically due to the interplay of internal electronic energies and vibrational ionic entropies. So all these phases are very close in energy. And so to discriminate them, you have to use very accurate methods if you'd like to do this in theory. And these very small energies are then shifted, are displaced by entropies, vibrational entropies of quantum protons in the compounds. And so the phase boundaries are very delicate and fragile. So to determine these phase boundaries, what we need in theory, we need an accurate evaluation of electronic internal energies, as I mentioned. And so this basically is translated, if your background is more on chemistry, in the full account of electronic correlations, because you know that the full account of internal electronic energies means that you have to solve exactly the Schrodinger equations for electrons. So you have to go beyond Hartree-Fock or DFT related theories. And so you have to basically fill the gap between the total energy and the Hartree-Fock energy. And the gap between the total energy and the Hartree-Fock energy is the correlation energy. So the second point is that you have to provide an accurate treatment of the ionic degrees of freedom and including them in a quantum way to provide a full account of nuclear quantum effects. And then there is the third point, which is maybe the most interesting for the physics of these compounds. This is the non-trivial interplay between the electronic degrees of freedom and the nuclear ones. And sometimes you have to go beyond the Born-Oppenheimer approximation and to include a truly non-adiabatic dynamics. This is particularly true for superconductivity. Superconductivity is a genuine non-adiabatic phenomenon, so you have to use a non-adiabatic framework. For hydrogen bonds, instead, you can still use an adiabatic framework, but you have to deploy a full inclusion of electron correlation and the full inclusion of nuclear quantum effects. I'd like to mention that a modelization based on, if you like, low energy Hamiltonians is sort of doomed to failure, because as you have seen in the phase diagrams, we should spend a wide range of pressure and temperatures. And so you have to be able to follow the variation of the properties on a wide parameter range. So an ab initio approach would be highly beneficial and desirable. And so we try to develop this framework, this ab initio framework. So the electronic internal energies have been treated in our framework by the quantum Monte Carlo wave function, which is a highly correlated many-body method, as Dario introduced very nicely before. The second point is, what about ionic degrees of freedom, okay? And so to include quantum description, to provide a quantum descriptions of nuclei, we ended up to use a molecular dynamics in the path integral formulation, so a path integral molecular dynamics. Of course, temperature is fundamental, and to include temperature effects, we used a Langevin thermostat. So putting all these three ingredients together, we ended up with a combined approach, the path integral Langevin dynamics, driven by quantum Monte Carlo forces, published in this paper here 3 years ago. And I'd like to thank this point my collaborators who contributed to develop this framework: Félix Moi, a former PhD student of mine, Rodolphe Lemier, Marco Saita, and Sandro Sorella, who is the developer of the quantum Monte Carlo code we used. So now I'd like to, at the same time, explain the method and show the applications. So the applications I'm going to show you today are to the protonated water clusters. And at this point, it's worth thanking as well the HPC centers, which made this possible thanks to the CPU time allocation, as this is also an HPC school. So I think this will be appreciated by the audience. Okay, so application, the first one, the simplest, if you like, molecular system showing very, very large quantum nuclear effects, widely studied both theoretically and experimentally. So it's a test bed for novel methods in this field. It's the Zundel ion depicted here. So 2 water molecules bridged by a proton in the middle. Okay. So the electronic part of this system has been treated with the quantum Monte Carlo wave function, which has this complex form here. It's a product of the Jastrow factor and the symmetric part in red here. The Jastrow factor is somehow the same form as the one shown by Dario before in his framework that was developed using neural networks. In my framework, this is developed on a Gaussian basis set centered on the nuclear centers. And these psi are Gaussian basis functions. And those are used both in the Jastrow factor, which correlates pairwise electrons, and also in the determinant part, where now we are able to describe also correlation through a linear combination of Slater determinants. All right, so Dario was very keen in explaining the philosophy behind a stochastic integration in variational Monte Carlo framework, and this is exactly what I'm using here. So I'm evaluating the potential energy surface V of Q through a Monte Carlo integration of this bracket here. And not only the potential energy surface, but also the ionic forces, which are minus the gradient of this potential. Those forces are the quantities which drive any molecular dynamics simulation. And so I'm going to use these quantum Monte Carlo forces to drive the dynamics. And one of the problems faced by using very accurate potential surfaces, but determined in a stochastic way, is the noise of this V of Q. So the average V of Q is very, very accurate, but it's noisy. And this noise can be detrimental to stabilize a constant temperature MD simulation. To cope with this, Attacalite and Sorella developed a very clever strategy. So to use Langevin dynamics instead to exploit the noise in the determination of V or Q and also in the forces to thermalize the system. So
okay,
the noise,
5 minutes left.
Yes. So the noise, instead of being a negative issue, is a positive side, is a positive contribution, which helps in thermalizing the system through a damping term. So we use a Langevin scheme where now the random force coming from the noise is equilibrated and controlled by a damping term, a friction. And the relation between friction, the gamma term here, and the correlation, the noise correlation, is exactly the temperature through the generalized fluctuation dissipation theorem. So what about quantum nuclei? So quantum nuclei in this formalism are treated using necklaces. Why is that? Because we replace the quantum kinetic term operator in terms of a set of springs. Okay, and so these springs live in an imaginary time, which is basically the line which connects the ring here. So from a classical point-like particle, we got to a quantum particle, which is now a necklace. And thanks to the quantum to classical isomorphism, we can now simulate the necklaces as classical systems, but in an augmented space. The cost to pay is that we introduce another energy scale, which is the energy scale of the quantum springs. And this is a critical issue for all path integral methods, because this leads unavoidably to a slowing down of the simulation. We were able to solve this problem in a very efficient way by resorting to a joint momentum position coordinates, which leads to a formalism where now harmonic forces are included in the generalized friction. So we have both Langevin friction and interbead coupling, harmonic coupling on a single shot. So on a single shot, we are able to integrate both internal harmonic degrees of freedom and the Langevin friction. So this basically leads to a new MD scheme. We call this, we dub this path integral Ornstein-Uhlenbeck dynamics, PIOUD, because this basically is nothing else than a damped Brownian motion for the quantum part. Then we have to combine PIUD with quantum Monte Carlo. So PIUD gives you a new set of nuclear coordinates, and on the top of this new set of nuclear coordinates, you have to compute a new wave function, a new quantum Monte Carlo wave function for the electronic part, and so on and so forth. So this will provide new forces, which will lead to a new set of nuclear coordinates, and so on and so forth. So that's basically iterative procedure. To be effective in this, we ended up with some approximation, which basically we exploited the locality of the basis set to basically describe in a simpler way all bits in the same necklace with the same parameters wave function. But that's a very technical issue, and I'd like not to spend too much time on that. So applications, the Zundel ion, you can see the movie here. So what we checked, because what this was already known, is that the temperature behavior of the classical system, if you treated this classically with classical nuclei, is very, very different than the truly quantum case, which is the true system. You see here the upper panel. There is a strong temperature dependence, which is killed by quantum effects. So in other words, quantum effects prevail over thermal fluctuations up to room temperature. So room temperature, the temperature where we live, is a quantum situation for this class of systems, this class of quantum materials. So we included also the solvation shell. in this inner core, which is the Zundel, and this leads us to study a protonated water hexamer. Okay, so where now the solvation makes the system closer to a proton impurity in water, because at least the first solvation shell is included. And so we now run the simulation, the fully quantum simulation for these extended systems, and we have interesting results if we look at the pair distribution function between two oxygens here in the inner core as a function of the temperatures, and we have sort of if you like, a positive effect of the proton delocalization, the quantum proton effects to make the H bond in the inner core tighter in a given temperature range. And so that's also confirmed by the instanton analysis of the proton hopping. And so this work in preparation. So there is a very positive interplay between nuclear quantum effects and temperature in these systems. Okay, so let me conclude and summarize. So we introduced a new formalism to include both electronic correlation and nuclear quantum effects in quantum materials from first principles. We apply this to protonated water clusters. We'd like to apply this for also to hydrogen-based superconductors. The extensions, the outlook is to compute phonons as well with this frame, and also to couple the determination of QMC of the determination of the potential energy surface by QMC also with machine learning techniques. So let me advertise some job openings. So in my group, we can have PhD positions financed by the doctoral school Physics in France. We have postdoc positions thanks to a recent ERC project, the TRAX project funded recently. This will be a new center of excellence in exascale computing with a particular accent on quantum Monte Carlo stochastic methods. And then we could have permanent positions through the CNRS, and I remind you, for the interesting people, the deadline for applications is January the 7th, 2021. For next year. So if you're interested, please contact me at this email address. Thanks for your attention.
Thank you very much, Michele. Okay, so now the session is open for question. Okay, so maybe let me shoot my question because I'm not in the field and maybe. Okay, so there is something I would like to understand. So you say that even at 300K, okay, so the quantum effects, I mean, dominate or something like that. You said, okay, okay. Yes. If I remember well my lectures on condensed matter, when you consider, I mean, electrons in a material, okay, flowing, we know that we have this notion of a Fermi energy, and this Fermi energy in metals is very high. Okay, so the KT is very small. So in a way, you also see quantum effects in some way, because you have this fermionization, okay, right? The Fermi distribution. So do you have, I mean, some kind of the same notion here? That is to say that, yes, you see quantum effects because precisely, I mean, the KT is much smaller than some quantum scale?
Okay, so
energy
yes,
scale?
Yes. So basically, there are two quantum scales. Okay, so one is the scale for nuclei, okay, and the other is for the electrons. So if the Debye frequency for nuclei is as large as the Fermi energy, in that case you enter into a very exotic regime where basically both electrons and nuclei are degenerate. And so this system becomes then a two-component system, where you are, in other words, you are very, very far from the Born-Oppenheimer approximation, where you first solve the electronic part and then the nuclear part. In our frame, in this particular framework I presented to you today, we are still in the Born-Oppenheimer approximation. Okay, so the Path integral MD is run on the potential energy surface provided by quantum Monte Carlo within the Born-Oppenheimer approximation. So in other words, you won't be able to describe superconductivity within this framework.
Yeah,
okay?
okay, yeah.
Nor the exotic phase you mentioned, where the Debye frequency and Fermi energy would be close each other. It's not somehow very far from what happens in this new class of materials, these high temperature superconductors. In these new class of superconductors, the Debye frequency is very, very high. And so there is indeed a competition between the Fermi energies and the nuclear energies. And that's why BCS is basically at the borderline of being applicable. And this makes, in terms of the BCS theory, this makes another challenge I didn't mention in these slides, because it's another chapter of the story. BCS is somehow close to failure in these systems, and so then you really have to tackle them as a two-component quantum systems. But this goes beyond the method I presented today.
Okay. Any other questions? Okay, maybe I am also asking to a couple of questions. I mean, very simple. At the beginning, you mentioned about this superconductivity mechanism of at high pressure. Okay, so I have two questions. The first one is whether, I mean, the mechanism is well understood. Okay, and the second is, I mean, is it useful in a way? Because, I mean, you said, of course, I mean, we would like to have, I mean, superconductors, I mean, at room temperature, but with such high pressures, how could we imagine anything, I mean, possible from an engineering point of view?
Okay, so thanks for the question. The two questions, they're very important. So, is it understood? Yes and no. I mean, the yes and no depends on, if you like, the quality of the answer you'd like to get. Okay, just an example. This slide here, rare earth hydrides have been predicted to be superconducting with high temperature already in 2017 within a BCS framework with ab initio couplings, okay? And so that's a PRL here. But there is a caveat, because this has been predicted for yttrium H10, okay, from theory, while in experiments, this has been found in lanthanum H10, H12. You see, I mean, theory somehow grasps, the BCS grasps the physics, but to be predictive, it's very hard, okay? So what was the second part of your question?
About the engineering.
Oh yeah, okay, so yeah, the perspective. So the perspective are, for me, are very positive. Because, you know, imagine that. So in 5 years, we went from, let's say, from 200 Kelvin up to 300 Kelvin, okay? Just because there was a huge interest in the community in searching new hydrides. Now, of course, the interest is now you know, addressed not only to reach higher and higher TCs, but also to lower and lower pressures, okay? And that's maybe, this is a big question mark behind that, of course, but this could be possible by exploiting the chemistry behind the hydrides.
Okay, okay. And now, last question, really, I mean, because I find this interesting. You saw there was a curve in your slides around this one. I don't know if the following one or before, where you see as a function of the pressure. Okay, right?
This one?
Yes, this one. Yes.
Yes.
Do the people understand the cusp, so to say? Why
no, I don't think so. I don't think so. So this paper has been published in a rush. So it was one of the fastest publication, the fastest peer review ever. It has been sent to Nature, and after 1 week of peer review has been accepted. And I think this has been sent in a rush. I mean, you know, I mean, they just found this by synthesizing, you know, putting together ammonia and H2S together, and they found these. No, sorry, not ammonia, methane. And they found these amazing superconductivity. So in the paper, the structure is not clear. Okay, There are 5 Poletti structures, but they are very different. And it's not clear also if in the middle there are metastable phases. I mean, this cusp could be due to metastable phase. But it's very hard. The problem is that in terms of experiments, the structure is unknown. I mean, the hydrogen positions, unfortunately, are unknown due to the weak cross-section, X-ray cross-section of hydrogens.
Okay. Thanks.
You're welcome.
Any other question? So if no, I think we should thank all the speakers of today's session, okay? And all the organizers, of course, and Yvonne, who is not with us, no longer with us today, but she will be back tomorrow. Okay, she has been very instrumental in setting everything, okay, for you to listen to all the nice talks. Okay, so so we resume tomorrow, I believe. Okay, same time, Singapore time and French time. Okay, and the chairman for tomorrow's session will be Kwek Leong Tran. Okay, I hope he does not forget. Okay, and well, see you tomorrow, I guess. Any other message you want to pass?
Join you in thanking everybody, especially Yvonne, but I will say that also on the last day. And yes, let's all come back tomorrow at 8:30 French time and 3:30 in the afternoon Singapore time.
Singapore time. Okay.
Thank you, everybody. See you tomorrow.
Thank you all. Bye-bye.
Bye-bye.